Hello there, my name is Charles Wasfan Msipa. Welcome to another presentation of computation of limits. In this presentation, we focus on computing limits when x tends to plus or minus infinity. So we're going to discuss an example which appears in your study guides, and another example that which I got here for you so that you can try to develop your skills in computing this type of limits. So let's look at this example. We've got here a limit of this rational expression as x is tending to infinity. We need to evaluate this kind of limit. Now, whenever you are dealing with limits as x is tending to plus or minus infinity, we need not to lose sight of the fact that if we've got an expression 1 over x, which we know a hyperbola, if we know that as x in this expression is tending to plus or minus infinity, this expression will tend to 0. And you can see it graphically when we have a graph of a hyperbola this way. We know that it decays here very fast, going down to 0, and this side it actually starts from minus, it is close to 0, and it goes that way. So as it goes to minus infinity in this direction, you can see the graph approaches the horizontal axis, which is 0, axis where the value of y is almost equal to 0, and this side also something similar happens. So now, if we're going to evaluate this limit, like I've said, we must never lose sight of this kind of expression. Maybe let's rewrite it again here this way, that we put 1 over x. So this 1 over x will approach 0 as x is approaching plus or minus infinity, as illustrated in this graph. So how do we use that idea here? So what we're going to do is we're going to combine this idea and some kind in the factorization actually. So what kind of factorization are we going to do here? We will always look at the two polynomials, the numerator and the denominator, and try to identify the highest power of x. Now it's the highest degree of x which appears in the expression. And then we try to take it as a common factor. And remember, if we've got an expression a, b plus a, c, if we take a as a common factor, you write it outside the bracket, and to get what remains in the bracket here, you should divide each term by a. Then when you divide by a, you're going to get b, and here by dividing by a, you're going to get c. So once we've identified the term which has got the highest power of x, we'll take that highest power of x as a common factor. Then we'll divide by it every term like we've done here. Then we'll try to proceed calculating the limit and see whether we can get our limit. Because we notice first of all that if we would evaluate this expression as x is going to infinity, we'll get to an indefinite undetermined expression of this nature. So again, when you get this kind of expression, you must reflect and see that if you get an indeterminate situation of this nature, then after that you have to proceed and identify the highest power of x. Like here you can identify that the highest power of x is x power 4, and there is x power 4. So wherever we identify the highest power of x, we would actually take that as our common factor and do this kind of division. So in this case, this is going to lead us to calculating limit as x is approaching infinity of the expression is going to look like this. If we take x power 4 here as a common factor, we write x power 4 outside the bracket, divided by x power 4 here, we'll get 9, plus dividing here by x power 4, we'll get 1 over x squared. And I hope we notice here that if we compare 1 over x with 1 over x squared, we would actually see that 1 over x squared will approach 0 faster as x is going to plus or minus infinity. So we can take note of that. So in denominator, we're doing exactly what we've just done in numerator. We'll draw out x to the power 4 as a common factor, and then in brackets we're going to have 2 because we're dividing it by x to the power 4. Then we're going to have 5 over x to the power 2, and then minus x over, so not x, x over x to the power 4, which simplifies to 1 over x to the power 3. So we write here 1 over x to the power 3. Then coming to this last term here, we're going to have 6 over x to the power 4, and work that. Now, once we have done this, I hope you notice that this x to the power 4 and x to the power 4 here will simplify to 1. Then the remaining expression, equivalent expression will be limit as x is approaching infinity of 9 plus 1 over x squared all over 2 plus 5 over x squared minus 1 over x cubed plus 1 over x to the power 4. Now, as you can see now, we've got rational expressions of this nature, differing of course in the powers of x in the denominator, which just the higher the power is, we expect that expression to approach 0 faster. So what will happen here now when we calculate, we will let x approach infinity. By this kind of, with this kind of understanding, we'll see that this expression here will approach 0, and then coming to the denominator, this one also will approach 0 actually faster than any other. I'll just indicate with the arrows there that this is going to 0 at a faster rate, and then this one will also go to 0, and this will approach 0. Now, if all this approach 0, so what we actually have here, we're going to have 9 plus the limit there, which is 0, over 2 plus these are the limits, which are 0 plus 0 plus 0, which will also be 2 plus 0. And we can see that this is not anything similar to that. Then we can give that defined number 9 over 2 as our limit. I hope you understand the strategy which we have followed here. The most important thing is to have this, not losing sight of this kind of limit, and then coming to the expression, identifying the highest power of the x, and then extracting it as a common factor. Normally it will simplify like this or in a similar way, such that you'll be able to calculate your limit. Now, our next example is also an example, similar examples you'll find in your Study guide, we've got here x to x squared plus 7x under the radical sign minus 4s as a denominator of 3x plus 5. Now, to solve this kind of a problem, we also need to manipulate somehow that we can be able to evaluate the limit. Now, what we're going to do here is the following. We can see that when we substitute here, well, this expression under the radical sign is going to grow and grow. Then also the 4x here will be somehow turning to infinity. So we end up with some kind of undefined expression which is more or less similar to minus infinity, infinity minus infinity. So now, to avoid that kind of undefined situation, this is what we're going to do. Then what we're going to do here, we're going to extract a common factor within these two terms. Then we'll write this as follows: limit as x is going to minus infinity of this kind of expression, 3x plus 5. I hope you notice that when you get this kind of thing in the denominator, we also be having some kind of infinity in the numerator there, which is, we can see that it's not a defined entity, the whole rational expression here. So then what we're going to do here, we just said we're going to check out common factor x squared for these two terms, which was then as x squared brackets 1 plus 7 over x minus 4x. Now, once we've done that, we remember that the square root of a times b is equal to square root of a times square root of b. So if you apply that here, we're going to get the following expression: x tending to minus infinity here. We're applying that, take our a to be x squared and our b to be this expression 1 plus 7 over x. Then we've got the following. We've got 3x plus 5, and then here we've got square root of x squared by square root of 1 plus 7 over x minus 4x. Now we recall that also square root of x squared defines what we call the absolute value of x. And then what we can now, well, we can write this expression as limit as x is tending to minus infinity, the limit of 3x plus 5, and then we write this now as absolute value of x multiplied by the square root of 1 plus 7 over x minus 4x. Now, we notice that x tends to minus infinity, which actually means that x is less than 0. Then we'll note that absolute value of x will then be equal to minus x. So now we can transform this expression to limit as x is approaching minus infinity, 3x plus 5 over minus x multiplied by 1 plus 7 over x minus 4x. Now at this stage, I'll draw your attention to another manipulation we're going to do now on in numerator here, and we're going to do it this way. Well, let's write this as limit as x is tending to minus infinity. What we're going to do again here, we're going to take out x as a common factor in the numerator, and then we've got 3 plus 5 over x brackets all over minus x multiplied by the square root of 1 plus 107 over x minus 4x. Now, if you look here in denominator, we also have a common factor minus, we can say minus x, we can select minus x here and there, or just x is fine. In this case, we're going to then write, in the next step, we're going to write this as limit as x is approaching minus infinity. And now if we draw this common factor x here and there, it's going to simplify to 1. Then we'll be left with an expression which is 3 plus 5x over minus 1 plus 7 over x minus 4. Now, if you look at the manipulation which we've done here, we're actually again driving towards having some kind of expression which is 1 over x, which we noted that it tends to 0 as x tends to plus or minus infinity, which we have there and there, because 5 and 7 are constants. So as x tends to minus infinity, this denominator becomes in absolute bigger and bigger, and then the fraction as such will shrink towards 0. So from there now, we can now say this tends to 0, like this one also tends to 0. So what we're going to be left with there, we're going to be left with 3 over minus the square root of 1 minus 4. And as you can see, square root of 1 is 1, then you put minus 1 minus 4, and then we can now give our limit as 3 over, or this is minus 3 over 5. And then at that point, we would have finalized our determination of the limit of the expression which was given here as 3x plus 5 over the square root of x squared plus 7x minus 4. In this case, you can see as x is tending to minus infinity. I hope the strategy which is used here is clear, and now I'm going to, in the next presentation, present another kind of limit which involves a radical sign like this, but a slightly different strategy, so that you can also develop your skills in that direction of evaluating limit. Others for now, thank you for listening.